So today we're going to be evaluating a very interesting limit. It looks pretty exotic. We've seen gamma functions and digamma functions before in limits, but zeta functions are kind of rare. And this limit is actually related to what is called the principal value of the zeta function at s is equal to 1. And actually, the exact value for the principal value is just 1/2 this. Now, the principal value is something that you can search off Wolfram, not Wolfram, but like Wikipedia or something, and you get a very quick result, and you know what this evaluates to. But that's not interesting. So I want to evaluate this in a sort of from scratch way that doesn't require any sort of prerequisite knowledge. So first of all, this has a very interesting form because if you were to plot the Riemann zeta function, the analytic continuation of it, it actually I'll draw it out. So you get like this is the xy plane, and then it has a sort of vertical asymptote at s is equal to 1. So this line is here is s is equal to 1, and it has, well, first of all, an asymptote, which means it goes off to infinity, but it also when s is less than 1, it's actually negative, and it actually goes something like this, and it kind of just oscillates around 0. So this is kind of what it looks like, right? It has a sort of 1 over s minus 1 look to it, and that's kind of the inspiration of this, because what this is basically doing, it's taking 2 points which are reflected about s is equal to 1, and it's taking the sum of those two, and it's infinity minus infinity. It's, whoa, it's very interesting. But once again, this is like already known knowledge, so like you could just search it up and you get the answer. So how we're gonna evaluate this? First off, we want to do, we have 2 zetas here. We don't like that. We want to change it into 1 zeta. So what I'm gonna do, first of all, I'm gonna change this s here. So I'm gonna take some number t is equal to 1 plus s. So this is now the limit as t approaches to 1 of the zeta function evaluated at t, and then plus zeta function 2 minus t. So this is just if you plug in t is equal to 1 plus s into this, you get this. So what we're actually going to do, we're going to remove the singularity. We're going to add something and then subtract something, such that we can split this up into 2 reasonable limits. So what we're going to do, we're going to add on and subtract from this limit 1 over t minus 1. We have zeta of t. Let me think if this is plus or minus. I think it's like I think it's minus. Yeah, I think it's minus. Minus 1 over t minus 1. And then we're then going to do the same for this. We're going to do plus zeta of 2 minus t, and then, well, plus 1 over t minus 1, but I'm going to write it minus 1 over 1 minus t. You'll see why in a second. Okay, so let's split this up into 2. We have this one here with these 2, and then this one here with these 2 as well. So we have now the limit as t approaches to 1. First of all, we have this first limit, zeta of t minus 1 over t minus 1. Okay, this is the first limit, and then minus the second, assuming both converge, which we'll see in a second they do, they converge to some value, plus the limit as t approaches to 1 of, this is zeta of 2 minus t, zeta of 2 minus t, and then minus 1 over 1 minus t. Now, we want to change this so it looks like this, right? So because right now we still have 2 zetas. So what we're going to do, we're going to kind of go back. We're going to set s is equal to 2 minus t. So in this case, well, s is still going to 1. So we have s is going to 1 of 2 minus t becomes just s. So if s is equal to 2 minus t, 1 minus t is 1 minus 2 plus s. So 1 minus 2 is What? Yeah, 1 minus 2 is negative 1, so we have s minus 1. Okay, so these two are in the same form. This one has t as the variable, this has the s as the variable. So we can combine these. So we get, I'm just gonna write it here, I suppose. We're gonna combine these two, and then what we actually get is just twice this. Twice this limit. And this limit is something that we've seen before on YouTube and on sort of other math websites. And this is quite a famous limit, and it has a very interesting form to it, which you've probably also seen before. This is equal to 2 times the limit. This is not how we're going to evaluate this. I'm just pointing this out. T approaches to 1. This is, if we use the sum definition of these two, this is actually the sum of sum n is equal to 1 up to infinity, I think. And then it goes like 1 over n to the t minus 1 over t to the n, or I think it's something like that. It's a very visually pleasing limit, but this is not how we're going to evaluate this. This is irrelevant. So how we're actually going to evaluate this, this one we're still going to consider the sum, but this one we're actually going to turn it into an integral, because this is 1 over t minus 1. This is equal to, we're going to plug in an integral definition. This is x to the t minus 1 over t minus 1. This is evaluated, x is equal to 0, and then x is equal to 1. So if you plug in those, you get 1 over t minus 1. And then we get, after we take the derivative of this and then plug in integral bounds, this is the integral from 0 to 1 of x to the t minus 2 dx. Right, so this is just basic sort of antiderivative integral stuff. You've probably done this before. I'm going to erase this. We're going to plug in this integral for that, and then this sum definition for this. And then you get, this is twice the limit. Okay, this is t approaches to 1 of the sum, and it's starting from 1, and then it goes on forever, 1 over n to the t. Okay, and then this is minus the integral. I have, sometimes I say things awkwardly. So we have the integral from 0 to 1 of x to the t minus 2 dx. Now what we're going to do, this sum, so we have a sum here, and then an integral here. We don't really like that because we can't really combine them, we can't really do operations on them. We can only just leave them as it is. So what we're actually going to do, we're going to turn this into an integral. Okay, hopefully I'm saying that right. Turn this into an integral. So the sum n is equal to 1 up to infinity of 1 over n to the t. This, we can write this as the sum n is equal to 1 up to infinity. This is basically times 1, so 1 over n to the t. And then we're going to do the integral from n to n plus 1 of 1 dx. You can see how this is true because the antiderivative of this is just x, and then plug in n plus 1 minus n is just 1, so it's the same. So what we're actually going to do, we're going to drag this in. But we're going to make a notice. We're going to notice something, and this is why I chose these as the bounds. When n is less than x, I think it's actually less than or equal to x, less than n plus 1, the equals to, we don't really care because it's a continuous summation, the integral is, and so it doesn't really matter. When this is in this range, the floor of x, this is equal to n. Right, so this is just by definition of the floor function. So we can put this here. We have the sum. This is n going from 1 up to infinity. This is integral from n to n plus 1 of 1 over the floor of x to the tth power dx. And now we can just sum this. So this is the integral from 1 to 2, and then from 2 to 3, and then from 3 to 4, and then you're basically summing this thing up. So in the end, you can combine all of those integrals. You just get 1. From 1 to infinity, 1 over the 4 of x to the t dx. Right? Okay, so we've turned this into an integral. Nice. So we can now plug this in. This is now equal to twice the limit as t approaches to 1. We have, first of all, the integral from 1 up to infinity of 1 over the floor of x to the t dx. Right? And then we have the second integral. And this one is a different bound from 0 to 1. And we don't really like that. We want to change that. So for the second integral, we're going to use inversion. I think that's what it's called. It's just when you do 1 over x as a substitution. So if you let we can't use t. If we let y, because I refuse to use u, I do not like to do u substitutions because everyone does that. It's not cool. So we're gonna let what did I say? It was like y, I think. Y is equal to 1 over x, and then x is equal to 1 over y. Just okay, this is trivial. Dx is equal to negative 1 over y squared. Again, trivial. It's just the derivative. And then we're gonna basically plug this in. So this is integral from 0 to 1 of x to the t minus 2 dx. This is equal to the integral from, if we plug in 0, we get infinity, but we have this negative sign, and we can use that to switch the bounds. So this is infinity up top, and then 1 over 1 is 1 at the bottom. Nice. Okay, so we have the same balance. That's good. And then this is y to the 1 over y to the t minus 2. But then we have this 1 over y squared. So we can combine those dy. We can combine those. Minus 2 and then this y squared will cancel. We just get minus the integral from 1 up to infinity. We just get 1 over, 1 over y to the t dy. And here, I'm going to combine these two. So actually, if you ignore that this is x and this is y, this is in a very interesting form. We have floor of x to the t in the denominator, and in this one we just get x to the t. Okay, so this is all very cool. We get twice the limit as t approaches to 1. We have this this integral from 1 up to infinity of this. Okay, and then we get 1 over floor of x to the t minus 1 over x to the t. Nice, dx. And now we can just plug in 1 to each of these. So I'm just gonna directly do that. I'm not gonna waste space. So we have twice. Okay, this is twice the integral from 1 up to infinity of 1 over the floor of x. Is it the floor of x? Yeah, it is the floor of x minus 1 over x dx. Now this is a very interesting integral, actually. And maybe you can already tell what this is going to evaluate to. What we're going to do another limit, but this time it's this limit to infinity. So this is equal to twice. Okay, this 2 is very annoying, but it's very crucial. The limit as n approaches to infinity, and I'm using n here because n is an integer. Basically, we're taking an integer sequence and we're taking the limit of it. This is going to be the integral from 1 up to n, 1 over floor of x. And since this isn't an improper integral, right? So these two, we can split them, dx, and then minus the integral from 1 to n of just 1 over x dx. So this is our new limit, right? Okay, and it's an integer, which is important for this term, because for this one, we can now break this up into, is it like n minus 1 integrals. So this we have 2 times the limit as n approaches to infinity. We have this sum. We cannot use n now, so we use k equals to 1 up to n minus 1 of the integral from k to k plus 1 of 1 over floor of x. Okay, but once again, oh, this is dx. But once again, when x is between k and k plus 1, the floor of x is just k. So this is just 1 over k as our integrand. So this is a constant, we can drag this out, but then we get just the integral from k to k plus 1 of 1 dx, which is, well, just 1. I've talked about this before. So this entire sum is just going to be, 1 over k. Okay, this is very cool. And this is a very interesting sum because this is the harmonic numbers, harmonic series, the harmonic what is it called? Is that just I think it's just harmonic numbers. So this is h for harmonic, n minus 1. So this is very interesting. Now for this one, this is a very simple integral. You've done this thousands of times. This is the definition of the natural log. So this is minus natural log of n. This is, once again, these are sort of, it's kind of trivial, so I'm not going to explain this. Now, this is very interesting. This is a limit that should definitely look familiar to you. The only problem is the limit you've seen before does not have this n minus 1. So what we're going to make this n, so, and then we're going to have to subtract, because I'm going to remove this section. This is the sort of, yeah, okay, well, whatever, forget it. So basically, hk is equal to the sum, n is equal to, n goes from 1 up to k of 1 over n, right? So this is the harmonic sum. So what this is basically 1 plus 1/2 plus all the way up to 1 over k. So now we can consider h of k minus 1. And h of k minus 1 is this other sum. I'm not gonna write the sigma notation. I'm just gonna say this is 1 plus 1/2 plus, and this is all the way up to 1 over k minus 1. Now what I'm gonna do here is I'm going to subtract 1 over k from this. So this is minus 1 over k plus this. This gets rid of this term. But what is the previous term before that? That is 1 over k minus 1. And now these two are equal, right? So h of k minus 1 is equal to h of k minus 1 over k. Remember, we have n minus 1 here. And we want to change it to n, so we have to subtract 1 over n, this 1 over n limit. Now we can separate this limit and this limit, assuming they both converge, which they do, right? The limit as n goes to infinity of 1 over n goes to 0, so that doesn't matter. We can sort of ignore that. And we just get this. This is the limit definition of the Euler-Mascheroni constant. In YouTube lingo, in YouTube math lingo, we call it the Euler-Mascheroni constant, which is much more pleasant to pronounce. And it is written gamma. So this is twice times this gamma. And that's it. That is the value to this limit. I would say this is probably a pretty interesting, not interesting, this is probably a very quick solution, I would say. I don't know, I haven't seen many solutions, but this is the one I came up with, and it equals to this. Now, at the beginning of the video, I said that this is related to what is called the principal value of the zeta function, which is, it's basically like this thing, but over 2, right? It's the average of zeta 1 plus s and 1 minus s. So the principal value of zeta, which I think it's written PV, I think. Principal value of zeta of 1. This is just twice this, so no, this is 1/2 this. So this is equal to the limit as s approaches to 0 of zeta of 1 plus s plus zeta of 1 minus s. Is my handwriting going? Oh, my handwriting is going down. I don't know. Over 2. This limit is just equal to this Euler constant. That's what I'm gonna call it. Just Euler constant, gamma. I think I'm writing gamma the wrong way. I think this little going down thing should be on this side. But all right, so that's it. That is the derivation of the principal value of zeta of 1. So I hope you guys enjoyed this derivation. I think it's pretty cool. I came up with this, so I think it's pretty cool. And I'll see you guys in my next video.